Welcome to this session on directional well path design. This module is divided into two sub-modules, and today we are focusing on sub-module 1. We'll introduce the fundamentals of planning a directional well bore, covering trajectory segments and the main well types, while highlighting how design choices impact operational success. The objective of this sub-module is to introduce the foundations of directional well path design. By the end of this session, you should be able to list the main segments of a deviated well bore and explain the role of casing in supporting well integrity and directional control. We will cover how to select casing points, emphasizing that casing must be set in competent formations to ensure fracture resistance and effective zonal isolation. You will also learn how to choose an appropriate kickoff point, KOP, in both directional and horizontal wells, considering formation strength, trajectory requirements, and re-entry constraints. The session also explains the design of curve and lateral sections, focusing on inclination ranges that promote effective hole cleaning and minimize torque and drag. Finally, this sub-module will review the three fundamental well types: vertical, J-shaped, and S-shaped. These represent the building blocks of trajectory design. More advanced designs and considerations will be addressed in sub-module 2, but for today, our scope is limited to well segments, casing design, kickoff criteria, and these three profiles. Understanding wellbore segments is essential for designing a safe and effective trajectory. Rig floor datum, the zero reference for all measured depths, ensuring consistency in surveys and logs. Well reference point, WRP, the starting location vertically below the rig, providing the baseline for trajectory planning. Kickoff point, KOP, the depth where deviation begins. It must be in competent formation. Too soft and the bit washes out, too hard and the formation resists deflection, reducing directional response. End of build, EOB, marks the completion of the build section where the tangent angle is achieved, setting the path for the next interval. Hold section, designed to maintain inclination. To avoid hole cleaning issues, angles should be either below approximately 40 degrees or above approximately 60 degrees. Angles between 40 to 60 degrees are problematic, often requiring corrective design changes. End of drop, a section where inclination decreases. Drop sections are challenging due to weight transfer, shock, and vibration caused by side forces. A rule of thumb is to keep drop doglegs lower than build doglegs. Target and total depth, the final reservoir objective and drilled length, where maximizing exposure and maintaining borehole integrity are the key goals. By planning each segment carefully, engineers ensure both technical feasibility and drilling efficiency. Casing selection in directional wells is vital for trajectory control and well integrity. A casing point must always be set in competent formation. The reason is that once casing is run, the shoe becomes the weakest point in the fracture gradient. If casing is set in weak rock, the shoe may break down prematurely, limiting the maximum mud weight that can be used. This can prevent reaching the next casing depth safely. In directional wells, casing in weak formations can also cause washouts around the BHA, reducing side forces and preventing the well from kicking off effectively. Competent formations provide the mechanical stability needed for deviation. After casing is run, it is cemented in place. Cementing provides zonal isolation, preventing fluid migration between formations and protecting aquifers. It also secures the casing, ensuring structural integrity. Once cemented, the casing allows higher mud weights, enabling safe progression of the well. In summary, casing is not simply a mechanical support, it is a design element that governs mud weight management, enables deviation, provides zonal isolation, and ensures the safe continuation of directional drilling. The kickoff point is one of the most critical design decisions in a directional well. Its depth and formation strongly influence the success of the trajectory. The kickoff point must be placed in competent rock so that the BHA responds effectively to deflection forces. Weak formations wash out and hard formations may resist deviation. Designing the kickoff point requires balancing curvature requirements and operational constraints. The kickoff point must allow the required build rate to intersect the target at the correct angle without exceeding the mechanical limits of the BHA, drill string or casing. In re-entry wells, cement placement behind casing and previously produced zones must also be considered. If a whipstock is required, a casing collar locator CCL log must be run to ensure accurate depth placement. Poor kickoff point selection can result in excessive torque and drag, difficulty achieving angle, or even failure to reach the target. Ultimately, the kickoff point sets the foundation for the curve section, dictating whether the well can achieve its trajectory efficiently and within mechanical limits. Correct placement reduces operational risks and improves well performance. The curve section links the vertical part of the well to the tangent. Designing this section requires careful consideration of dogleg severity, azimuth control, and torque and drag management. Initial doglegs should be kept low. This reduces sliding forces, minimizing the risk of key seating and casing wear, while ensuring torque and drag remain manageable. Remember, torque and drag are cumulative. Poor design early on compounds later challenges. The plot shown here is a TVD versus vertical section profile with no azimuthal turn, as confirmed by the survey listing. This highlights the importance of kicking off in the correct azimuthal direction. A poorly selected kickoff direction may place the well on an azimuth far from the planned target, requiring large corrections later. As inclination increases, the dogleg required to turn even a small amount grows significantly. Therefore, it is best practice to perform most azimuthal corrections early, while the hole is still close to vertical. This results in smoother geometry, less torque and drag, and a more drillable trajectory. The lateral section maximizes reservoir exposure and must be designed to ensure both production performance and drilling feasibility. Inclination is a critical factor. If the lateral trajectory falls between 30 degrees and 60 degrees, hole cleaning becomes problematic. This affects not only drilling efficiency, but also casing runs and the final well cleanup. To avoid this, inclination should be kept below approximately 30 degrees or above approximately 60 degrees. Sometimes this situation arises because the reservoir team provides multiple target points without considering the trajectory angle it creates. Engineers must review these plans to ensure the inclination is feasible and does not create operational risks. For horizontal wells, lateral length is determined by the reservoir exposure required to achieve planned production rates. However, longer laterals increase torque and drag risks. If the section is not designed and drilled correctly, torque limits may be reached before TD. This is where BHA design and drilling practices are critical. Smooth wellbores with optimized hydraulics and hole cleaning strategies reduce friction and allow long laterals to be drilled successfully. Vertical wells appear simple, but they present specific challenges. By design, they are drilled with 0-degree inclination, directly from surface to target. In reality, geological tendencies, bit design, and BHA behavior introduce deviations. A common phenomenon is spiraling. Rotary and directional BHAs often drill wells that spiral around the vertical axis, even if the inclination at TD is near zero. The well may look vertical on paper, but in reality, the trajectory has twisted many times. This spiraling creates issues when the BHA is pulled out of hole. The assembly, under tension, must be pulled through the spiral, creating overpulls. These overpulls can easily be misinterpreted as wellbore stability issues, such as hole collapse or pack-off. In truth, they are usually torque and drag effects caused by the spiraled well path. Recognizing this distinction prevents unnecessary remedial action. With the introduction of rotary steerable systems, it is now possible to drill truly vertical wells. RSS tools counteract natural BHA tendencies and maintain precise trajectory control. This reduces spiraling, lowers torque and drag, and simplifies casing runs. Vertical wells remain a fundamental part of directional drilling. By understanding their limitations and using modern technologies, engineers can achieve straighter wells with fewer operational risks. The J-shaped profile is one of the most widely used in directional drilling. The trajectory begins vertical, builds inclination through a curve, and then continues tangent to the reservoir, forming a J shape. The main reason for J profiles is often surface obstructions. These may be existing wells, facilities, or natural barriers that prevent the rig from being directly above the target. By deviating at depth, the well can still reach the reservoir offset from surface. Designing the J requires careful control of the end of build. The tangent should end either below 30 degrees or above 60 degrees. Tangents between 30 to 60 degrees create hole cleaning challenges, casing difficulties, and cleanup risks. If the tangent or sail angle falls in this problematic zone, a second build-up section may be required. This allows the trajectory to exit the poor hole cleaning window and land in the reservoir at a more favourable inclination. J-shaped wells are popular because they balance simplicity with functionality. With the right build rates and tangent planning, they can be drilled efficiently while providing reliable reservoir access from offset locations. The S-shaped profile includes both a build and a drop section, giving it its distinctive S-curve. It is chosen when specific conditions require more complex trajectory control. S-wells are commonly preferred for gas wells because they can improve zonal isolation during cementing. By approaching the reservoir at a lower inclination, cement can be placed more effectively around casing, reducing the risk of gas migration. The drop section, however, is the most challenging part. Weight transfer in dropping intervals often creates shocks, vibrations, and side forces on the BHA. These can accelerate tool wear, complicate steering, and reduce hole quality. A rule of thumb is to design the drop dogleg at about half the severity of the build dogleg. This reduces mechanical stress and improves drilling efficiency. S-wells are more expensive and technically demanding than J profiles, but when designed carefully, they provide benefits in terms of trajectory flexibility, reservoir access, and long-term well integrity, particularly in gas field applications. This slide reviews the objectives of Submodule 1. You should now be able to describe the segments of a deviated well bore, from the rig floor datum to the target and total depth, including the importance of casing points in competent formations. We highlighted why casing must be cemented for zonal isolation, and how KOP placement in competent formations sets the foundation for deviation. We also discussed how inclination ranges affect hole cleaning, and why trajectory planning must avoid the 30 to 60 degree zone. You should now understand the three fundamental well types: vertical, J-shaped, and SE-shaped. Each has design considerations, applications, and operational challenges. This submodule has been limited to these basics. Submodule 2 will go beyond this point to address more advanced design considerations and profiles. Thank you for your attention during this session on directional well path design. This concludes Submodule 1, where we covered wellbore segments, casing design, kickoff criteria, and vertical, J and S well types. In Submodule 2, we'll expand into more advanced profiles and design challenges.